So now everything is recording. Thank you so much to everyone for coming and for all those of you who are watching in the future. This is our system overview lesson where we'll just quickly be going through each of the systems and really talking about what they do as well as their associated subsystems where applicable. So to start things off, I will be passing things on to Phil to talk about the chassis. Phil, if you are speaking, we cannot hear you.
There we go. Hello. My friends, my name is Phil. I'm a chassis system lead as well as the composite subsystem lead. And I'm here to talk about the chassis system, to give you guys a nice little introduction. Chassis is a structure-based system where the main focus is driver safety. We got two subsystems here, frame, which is led by Sam, and composites, which is led by myself. The frame is concerned with safety and structure, with composites' main concern is aesthetic, comfort, and driver protection. There's also ergonomics, which focuses on the efficiency of the design as well as the comfort of the driver, which is what we optimize as well after the main design is finished, which is what we're going to be doing in Rev B. All right, next slide. So we got design of the frame first. For design, we're giving a set of rules from Baja, and we have to follow these rules in order to pass tech. This is because these rules are set in for safety. There are a ton of rules, and we have to make sure we follow them closely and accurately, or else we will not be able to compete, which means all of that work that we've done goes to waste. After that, we have some freedom, which we use to satisfy the needs of the powertrain and the vehicle dynamic systems. For example, we've got some upward control arm mounting tubes, which whoever is screen share can show on the bottom image. And we got some miter gearbox tubes that we're going to be using for our miter gearbox. And this is all done during using SolidWorks, like we said before. We do FEA on SolidWorks, which is the image on top, with all the colors. We do torsional rigidity testing, which basically shows how twisty our car is. Okay, Sam. And we also did the design on SolidWorks, which is all the tubes where they're all positioned. Yeah. What we're actually doing right now is checking the rules for our Rev A, because we went from Rev A, which is the first frame of car 20, and now we're currently at Rev W. So a lot of changes have been made, which you'll see in the next slide when we get there. But we have to make sure that all of our changes are good. If you guys do chassis, this will be your first task. I'm going to send you the rule book. I'm going to send you Rev W, and you're going to check all of these rules out. This is in order to get you comfortable with SolidWorks. I think it'll be a good use of how to measure using SolidWorks. And you'll also get to see the names of the tubes because they're all named. You'll get to learn the named points, which is important in the rule book. And yeah, this will help you in case someone's like, oh, can you do this for me? And you're like, oh, I don't know what the sims are. This way, you'll learn how to do everything. The SolidWorks part, that'll be figured out by someone else. That's not me. But to answer your question, but yeah, when that is figured out, you'll be getting the rules, and you'll have to check it. And hey, maybe you'll find something that we don't say. So yeah. All right, next slide. We got this blue frame right here. This is the car 20 frame, and the gray one is Rev W, which is what we're currently at. You can see there's a lot of changes. A lot. So yeah, you would be checking just to see if this all passes tech. We already did this check, to be honest, but again, it's good practice for you guys to learn the chassis as well as SolidWorks. Okay, next slide. Next, we have the physical fabrication of the frame. There's a lot of work to be done. A lot of help is needed. There's a lot of notching. There's a lot of jigging that has to be done. If you do chassis, you'll be thrown right in. You'll have a lot of work to do if you'd like, of course. If you don't want to do that much, we'll do as much as you'd like. But there is a lot of work if you're interested. This involves jigging, notching, cleaning of the tubes. Some of you guys may weld if you guys can weld. I can't because of Mech 225. Yeah, I didn't take Mech 225, so I can't do welding and all that. But yeah, you would learn how to use the Dremel. You would learn how to notch tubes. Yeah, so this is more of the fabrication of the frame. And then next, we have the best slide of the best subsystem, Composites, my subsystem. So Composite is I am a mech major. I just took Mech 226 because I was never told, because I joined the club. My first semester I joined the club, I took Mech 226. So yeah. But yeah, when we do fabrication, yeah, you guys will do it, but I can't. Composites is mainly a fabrication subsystem where you're involved in doing the seat, the body panels, the headrest, the stickers, and you're also involved in some seatbelt stuff as well. To give you guys a brief introduction, the seat is made out of carbon fiber, and if you want to make it red, you got Kevlar as well. This is done using a epoxy resin vacuum trap on the seat mold, which is a very long process, I'd say. We were very new to it this year. I don't think anyone knew how to do it. And let's just say it was very frustrating because we didn't know what we were doing at first. But towards the end, we got the hang of it, and I thought, well, you got the seat right there. The green stuff is a PVA, which washes out, and you got to trim it. But I didn't get a more updated picture. But the seat came out really nice, even though it was frustrating. But yeah, it's a really, really interesting experience. It was a cool process using resin, something I've never done before with carbon fiber as well. And yeah, that's the seat. Next, you got the body panels. Some of them we cut out using scissors, shears, and some of them for these odd shapes, like on the Sims, we use the thermoformer, which is a process learned in 325 if you're a mech major. This is used to, this is like heating up the plastic, and then you drop it onto a mold, and then using vacuums under it, it'll like suck it up, and then the plastic will become that shape of the mold. And yes, Max did help make the thermoformer, as he's pointing out. For composites, the body panels are there for protection of the driver. Rocks may hit them if there are no body panels there. And it also keeps out mud, which keeps the car nice and light, because I believe we added, I think someone told me 100 pounds of mud, which I don't believe, but that's I think what Henry told me. We had 100 pounds of mud added to car 14. And the seat is more for ergonomics. You don't want to sit on a seat for 4 hours. That really hurts. And yeah, you want to sit on something comfortable. So our mold is designed for no one. Like, it's just a universal mold, but we do try making it as comfortable as possible. All right, and that's it for composites. Next up, powertrain. No, Mech 226 is not useful. You can learn it in iCreate.
All right, well, hey, my name is Christian Funes. I'm the powertrain system leader. So I'll be going through powertrain. So to begin off, what is the objective for powertrain? Basically, make car go. That's literally it. And so here we have four major subsystems. There's gearbox, drive shaft and axles, CVT, and then the intermediary. And basically, powertrain really does it all. We do everything from designing, fabrication, testing, and actually driving the car. So design work, there's always like something that needs to be calculated, something that needs to be catted up. There's always something that, you know, has to be done in order to get a preliminary idea, like in order to make a physical thing. And so then once we have that idea, we have to actually make it. So that's where fabrication comes in. So there's a lot of fabrication done in this subsystem, in the system. We use like basically every machine in the shop. And then finally, once we make it, we have to test it to make sure that our initial design wasn't crap and that it doesn't blow up. So that's basically a quick summary of the whole system, and then now I'll go into the subsystem. So next slide. Okay, so starting off, we have the gearbox. Okay, so the gearbox subsystem has everything and anything to do with gears in boxes, and that's basically a big umbrella for the whole subsystem. We have the rear gearbox, we have the miter gearbox, and then we have the front gearbox. So with this new rule set, where they're requiring us to do four-wheel drive, we are including 4 new gearboxes into the car. And so with these, there's going to be a lot of fabrication work that has to be done and a lot of design work still, because some of this stuff, it still has to be changed up for another revision that we're planning on doing. For example, with our Rev B, we want to switch the miter gearbox to be under the engine instead of to the side of it. So there's some design work that needs to go in there. So that's something that people can be help out with. And then so there's also a lot of testing that has to be done, because most of these components, since we've just been away from school and actual like in-person stuff, we still have to test these things. And then there's also like stuff like FEA. So if you can see on the right of the slide in the middle, there's that colorful part. That part isn't colorful in person. That's just an analysis of the part. So basically what we do is we take the part and we tell it where it's going to be held down and where the forces are going to be applied. And then we can see if it's going to fail under these loads or actually be safe under the loads, in like, given the material properties of whatever material we use. And then currently, also as a final note, there are 2 gearbox subsystem leads, because there is just so much to do. And yeah, that's a quick general overview of gearbox. That's what we have. Next slide. And then next we have the drive shaft and the axles. So with the addition of all-wheel drive, we now have a lot more axles and drive shafts that we have to deal with and fabricate and test and design. And so previously, where we only had 2 axles powering the rear wheels, now we have about like 6 axles on the car and 6 like axle/drive shafts. So there's a lot of fabrication work that needs to get done with that. Also, we're looking into redesigning these axles, because some of them are just not optimal for fabrication. So we need to like look into new solutions, different ways of making these things. So there's a lot of design work there to do on that. There's also FEA, because the weakest part on some of these things are the tubes. So we have to make sure we definitely know for sure what type of torques these tubes can see. And then yeah, that's really it for this axle stuff. It's pretty interesting. It's one of the coolest ones, because the fabrication work, in my opinion, is pretty fun. But yeah, that's pretty much it for drive shaft and axles. Next, we have the intermediary. So the intermediary subsystem is responsible for the intermediary belt box, or the intermediary for short. The intermediary is meant for the axis of to move the axis of rotation of the drive shaft from the side of the car towards the center, so that we can more easily send power to the differential. The intermediary subsystem does a lot of work with timing belts, shaft design, case design, and to ensure that the power can not only be safely delivered, but that the belt box can occupy minimal footprint, because it's pretty small. It has to be pretty small, fits between the firewall and the driver's seat, so there's not really that much room there. It's about like this big. Got to make sure it fits inside there. So it's a real packaging challenge, So it's pretty cool. Really get your brain going. And then there's also some changes that need to be made for Rev B, depending on what we take out or leave in for the next revision, based on what designs are actually feasible. There's also, once we're actually able to manufacture everything, we'll need to do a good amount of testing on this stuff on various aspects, because a lot of the stuff, these belt boxes, we haven't really used before. We use something on a CVT pretty similar, but not exactly the same. So there's still some stuff we have to learn, some stuff that we have to double check, make sure we did correctly, And yeah, that's basically it for this, for intermediary. Finally, we have CVT. So CVT is basically the testing like clan. So what CVT stands for is continuously variable transmission. this is the brains of powertrain. What this basically does is it takes every gearing that we need into one small form factor. So instead of having a large clunky gearbox with only a certain set of gears, we have this wide range of gears with this nice small packaging. We buy this from a company called Gauge Engineering. They basically just sell this one part to Baja teams. That's like their entire business. So it's pretty much exactly optimized for our setup. It really, really is. But since we buy it, that means there's no manufacturing, there's no real design here. There's some design in cooling, because we do need to keep these things cool. You know, if you can imagine something like this in a big box and closed off, that box is gonna like basically encapsulate all that heat. So we really need some decent ideas with cooling. It's one of our biggest problems, because once we don't cool it, we have big issues with efficiency, and sometimes the belt will just straight up slip. So yeah, this purchase this. Okay, so back to testing. Testing on this CVT, we have two ways of testing primarily. We use a dynamometer, which basically means throwing a CVT onto a motor and a generator and figuring out what the torque curves look like. Or we could take this out onto the field on the car, actually test it, which they do a lot. They do both of them a pretty decent amount of time. So if it's either working in the shed with this engine going and running and then trying to figure out these torque curves with a whole bunch of different configurations, or if actually driving the car, getting out there in the field, it's a little bit more fun. But yeah, if anything, they're definitely the team that that gets to drive the car the most. But yeah, this subsystem is pretty cool. There's some design work with the coolant, like I said, and there's definitely of opportunity to like getting the car out there in the field and seeing it. Okay, I know I haven't really read the chat, and I don't know if there's anything for me to. I see. Realize about box. Do. Okay. Yeah, okay, so that's basically all we have for powertrain. If there's any questions or you guys are interested in anything, you can always let somebody know. And then, of course, they will just redirect you to me or anyone else that's like, that could get you involved. So thank you very much. And I guess I'll hand it off to the next vehicle dynamics.
Hi, everyone. I hope you can hear me, but I'm Neha, and I'm the Vehicle Dynamics System Lead. So vehicle dynamics is basically steering, suspension, and brakes. So this system is really just responsible for the handling characteristics of the car, as well as how the car responds to driver input. And the first subsystem that we're going to be talking about is the steering subsystem. So first, I also have like pictures in the later slides so you can see more of what I'm talking about. But first you have the steering wheel, which obviously the driver turns, which rotates the steering column, and that turns the pinion and the rack and pinion set. So basically the rack and pinion that we used to purchase off of Stiletto, but we actually recently started making it ourselves. So the ratio that we use is 6.4 to 1. And what that means is basically how many degrees you're turning your steering wheel versus how many degrees your tires are actually turning. So the higher the ratio that you have, the easier it is to turn the steering wheel, but then your hands are going to start crossing over. And obviously you don't want that to happen when you're racing because you have wrist restraints on and it's just not very practical. So for this reason, we chose a ratio that's not too high, but also not too low. And also for our steering column, you can kind of see it on the picture right now, but we're using U-joints for our all-wheel drive car. And basically what the U-joints do is it breaks up the steering column so you don't have one single tube, but you have multiple parts that are just reconnected. This really just allows you to move the rack and pinion system wherever you want, which is really, really good for the all-wheel drive car, especially because the front is kind of like a battle zone between steering and powertrain because everything just wants to be in the same place. So with the U-joints, you can kind of just move the rack and pinion out of the way of the differential and everything like that. So the rack and pinion is really just fundamental in transforming like the rotational motion to the linear motion. So obviously once the rack moves either right or left, that's going to kind of have like an impact on the tires because you have tie rods that connect to the rack and also to the tires. So once you rotate, that's kind of like the path that everything goes in. So in this system, we make most of the components. So there's a lot of manufacturing that goes on, except for things like the steering wheel and kind of just like the U-joints and stuff like that. So if you go to the next slide, you can kind of see more of what I was talking about. So that's a rack and pinion that we used to buy off of Stiletto. You can't really see the rack because it's covered by that boot, but we basically now make that. So it's a lot of CNC operations and EDM operations that go into that. And we also make the tie rods. So the ends we kind of buy off of McMaster and we can weld them onto the tube. But we like cut down the tube, and we used to be able to make, well, we used to choose to make the bungs, but now we're trying to stray away from that. And then on the bottom, you can see the steering wheel as well as the column. So you can see the U-joints a little better. The steering column is kind of broken up, and you can see that's not perfectly straight. So next we can go on to suspension. So suspension is responsible for mitigating the forces that the vehicle experiences. This is very useful, especially because we're going over lots of bumps and droops in the terrain. So this really helps a lot. In a whole, the suspension subsystem is responsible for the design, fabrication, and integration of a fully independent suspension system on the vehicle. So this consists of a short, long arm system in the front, which is basically an upper control arm that is shorter than the lower control arm. And we also have a multi-link system in the rear, which has 3 links consisting of the trailing arm and 2 lateral links, which I will show you later because that seems like a lot of big words that doesn't make sense. But basically in the front and the rear of the car, we use uprights that will connect these links to the tires. And another big part of the suspension subsystem are the shocks. So we currently use air shocks, which disperse the forces when you're going over things like bumps and droops. So we obviously can't really manufacture that. It's a little out of our comfort zone and our pay grade. But even though we don't get paid anything, but still. But we do manufacture a lot of stuff for the subsystem, like all the links and the uprights and the hubs. So there's also a lot of manufacturing that goes on here. So the steering and suspension really go hand in hand in providing desirable handling characteristics. So especially in the first iteration of our car, it was really hard to kind of find like that sweet spot between suspension and steering and making sure that everything is very harmonious. So definitely for the second revision of our car, it's going to be a lot of just making sure that everything is working well together. So on the next slide, so you can see the lower control arm and the upper control arm that I was talking about. Those go on the front of the car. And in the rear, you can see that underneath the shocks, you kind of have the trailing arm as well as the lateral links. So we use a different configuration in the front and the back. And that's kind of just what I wanted to show you guys here. Next. Okay, so the last subsystem is the brake subsystem. So we don't really manufacture much here, which you will see why later, but it's definitely a very important system because obviously you want the car to stop. So first you kind of have the master cylinders, which you can see in the left picture, which is kind of like a tank reservoir that holds the brake fluid. So when the brakes are pressed, the brake fluid travels through the brake lines and down to the brake calipers, which you can see in the right picture. The hydraulic pressure pushes the brake pads together, which are located between the brake calipers, and it squeezes the brake rotor and stops the car by stopping the rotation of the tires. In the front of the car, we currently have outboard brakes, meaning that the brake rotors and the calipers are located by the tires, while in the rear of the car, we have inboard brakes, meaning that the brake rotors and the calipers are on the chassis. So for the all-wheel drive car, we're currently looking into having inboard brakes in the front as well. So that's a big thing that this subsystem will be working on, especially when it comes to packaging and just picking out the different components. So most of this system the subsystem is purchased except for things like the brake rotor, which we designed but have laser cut by our sponsors. So currently we also have a 56% brake bias in the front and a 44% in the rear, which is basically just something that you can adjust and tunes how much force goes towards the front and the rear. So for all three subsystems, we do FEA, as well as a lot of testing on the car, static and dynamic. So we work a lot with electrical to make sure that we have like our strain gauges and all of the testing equipment set up. For Rev B, when it comes to vehicle dynamics, there's a lot that we're going to be working on, especially when it comes to steering and suspension, because we have to make sure that we get a lot of the geometry set up and we have really good handling characteristics. So that's a really big part, as well as optimizing the shocks, seeing if we can change into different shocks versus our old air shocks that we've been using. For brakes, we really want to work on a bias bar, as well as figuring out if we can use inboard brakes versus outboard brakes. So I don't know if this sounded like a lot of information, and if it is, like, totally reach out to me and I can explain it a little more. But that's basically what it is for vehicle dynamics. And if on your quiz, if they ask you what's the best system, I highly recommend saying vehicle dynamics, because nope, you're wrong. But yeah, that's basically it for vehicle dynamics. Next, we have electrical.
Hello, I'm Xiao and I will be talking about electrical. Okay, so first, let's talk about the things on the car, that being the brake light and the kill switch. So the brake light, it consists of a lithium-ion battery, 2 pressure switch, and an LED light. There is 1 pressure switch mounted on each of the brake lines, front and back. So when you press the brake pedal, the light will turn on. The battery is connected to the light through pressure switch, and in the circuit, the 2 pressure switches are parallel with each other, which means that when the brake light turns on, the brake light will turn on when either one of them is activated. And wires connecting the battery using ring connector, and wire connecting everything else using spade connector. By the way, transponder is part of composite area. Then let's talk about kill switch. We have 2 push button kill switch, one located at the left side of the driver and the other one located on the right side of the car. The kill switch connects the engine to the frame of the car, which serves as the ground. It connects to the engine using spade connector and connects to the frame using ring connector. When the kill switch is pressed, the spark plug is shorted to the frame, stopping the ignition and causing the engine to stop. Like the brake light, kill switch are also parallel with each other. Next slide. Next slide, yes. So, finishing with the things on the car, let's move on to the data acquisition part of electrical. The essential of data acquisition, being able to collect and store data, and there are many ways to do so. So how I always do it is I use an Arduino Mega. I will solder the circuit for the sensor and a micro SD card breakout board to an Arduino Mega prototype shield. So when I'm done, I can just slap the shield on Arduino and everything will be compact. I like Arduino because it's just simple, flexible, and most importantly, cheap. Alternatively, you can also use Raspberry Pi. In terms of hardware, Raspberry Pi outperforms Arduino. However, it's more complicated. Other than Arduino and Raspberry Pi, there are other devices that you can use for data acquisition, but they tend to be expensive, especially if you're looking for one that won't fall apart on the car. Anyway, regardless of how you collect the data, it should be stored in comma separate volume file or CSV file. It's basically a format where comma separates column and a new line separates row. This way, the file can be opened up on Excel and you can do whatever statistic you like. Next slide. Yes. Finally, we will briefly go over some commonly used sensors. The first one on the top, that one being the strain gauge. It changes its resistance based on the strain it is under, and it's used to measure the stress. Below that, on the right, we have linear potentiometer, which can be used to measure displacement. It is just a variable resistor whose resistance is correlated with displacement of the rod. Below that, on the left, we have a thermocouple, which as name states, measures temperature. It sends out a voltage when it experiences temperature change. And Hall effect sensor, the one on the bottom right, is like a magnet and can be used in multiple ways, but we generally use it to measure rotational speed. So this is it for electrical. Now let's have Dan to give us the overview for software.
Hey guys, so for software, one of the major projects this year is the DAC. As Zhao mentioned, we need to select a microcontroller. And whenever there's a microcontroller, there are people who need to program the microcontroller. There are multiple factors we need to take into account in the selection, like the number of analog and digital inputs and the built-in capabilities for data storage. So once we know all the necessary requirements of the system, we'll be able to select the appropriate microcontroller for our use case. We'll need to implement a storage solution for our data. Ideally, this will be a removable storage device where we can store our data in a CSV format, as mentioned by Zhao. So subsystem leads can import all of the data directly to Excel and analyze the results without any painful process. But in order to read anything meaningful from our sensors, we need to know how they're communicating to the microcontroller. Analog voltages need their own analog to digital converters, and digital signals will need to be interpreted properly. In all, this is going to require us to read a lot of monotonous data sheets, but it's imperative that we pay close attention and interface these components properly. Otherwise, our data will just be garbage. The data will then need to be processed, likely into ASCII text, so it can be stored in its file. So moving on to the suspension analysis program, this complex enigma will begin development once we finish our DAC. There are going to be three main components to it: the math, the user interface, and the render. These three components can be mostly developed independently so long as we have a top-down design that we're working from. The math, while very complicated, is very straightforward to implement. The complexity comes from the other two aspects. A graphical user interface, very often called a GUI, is a new type of programming paradigm where the program is running in an infinite loop, listening for events caused by the user. There's very little control that the software has over what the user does, so a lot of time gets put into error handling. The visual render is going to be a learning experience. We'll likely focus on this last, as I personally need to teach myself computer graphics, and by extension, I will be teaching all of our members and how to generate drawings with our tools. The end goal with the render is to conveniently give vehicle dynamics a visual representation of what we can expect the car to do and how we can expect the vehicle dynamic systems to behave. We'll also be using C for this project. C is the base of most of our modern programming languages, and it allows us to use multiple libraries, software development kits, and APIs and interface them all into the same program. As project size scales, it becomes significantly more difficult to manage these projects, so we'll probably wind up using a version control software like Git. The website redesign will be its own independent group working on this project, which could be going on concurrently to the DAC and the suspension software. As most of you have unfortunately experienced, our website can be a bit of a mess and unintuitive to navigate. This is less than ideal for a first impression. For this, we're redesigning our website to promote interactions with our club. To do this, you can use your preferred IDE and the program in the HTML, CSS, and JavaScript suite with any helpful or preferred frameworks. The design and implementation of the website will be open to the development team. the details on how this project is going to operate is still in the works, as it is highly dependent on who chooses to hop on board. So if this is appealing to you, please reach out to me and we can iron everything out. We'll be starting our education in next week's GVM. Of note for whoever is going through the slideshow, there is no education slide, so don't be confused. So for education, we'll be starting after next week's GVM, starting with the basics of the C language. I'll show you guys how to get set up with a development environment and the basics of a C program. Since both embedded systems and desktop applications can be made using C, this allows us to optimize education so that you guys have to spend less time learning languages and more time learning how to develop programs. In addition, C is one of the smallest usable languages out there, so you don't have to invest so much time into learning the language tools and features. You just have to learn how to use them. Even if you already know how to program in C, I still suggest attending these lessons so you can be learning these in the context of our club's operations. That's all I've got for you guys. So now I'm going to pass it over to Red so he can show you guys what's going to be going on with CNC and CAM.
All right, so CNC/CAM is the system that really deals with a lot more of the complex manufacturing of the car, especially when parts have too many complex geometries and contours, or maybe there's a lot of them to have to make. Machines often do it better. One of the reasons for this is that manual machines tend to only move linearly, so it makes things like arcs and whatnot almost impossible, if not very difficult to do. An example of what I mean by like they can only move linearly and can't really do arcs is, let's say in the hub over here, you can't really get away with doing a lot of these arcs, especially if you have like handles on your machine which only go like X direction, Y direction, and Z direction, because then you have to like be able to best approximate sine and cosine with your hands. That really doesn't work out, especially with other wackier complex geometries, like let's say for the gearbox case on the top right or the CVT backplate on the bottom right. Just doing it manually just becomes pretty much impossible. So that's where a lot of the automated machining comes in, and all of this is done through what's called computer numerical control, or CNC. And essentially machines that are outfitted with CNC capabilities are able to run automatically to at least some extent. In order to do this and make sure that the programs or the machines are running the programs properly, we have to run a computer-aided machining program. Essentially, you take a CAD model and import it into this computer-aided machining program, and you simulate all the tool paths. You specify like, oh, this has to be a 1/4-inch cutter, this has to be a spherical ended cutter, and then it'll generate the tool paths for you. What I mean by tool paths is generally just like where the tool moves and cuts. If you take a look at the bottom right image, you can see a bit more closely the tool paths that are associated. You can see how in this large section there are kind of like lines. That's basically the path along which the cutter traveled. And once all of these tool paths and stuff are specified, G code is generated, which is kind of a universal language for all CNC machines. So that in theory, if you create a G code file for one machine, it should be able to mostly run on another machine. And so with CNC and CAM stuff, we have at least over 30 unique parts. And actually at this point, I think it might be more because of all-wheel drive. And some of these parts require so much machine time, especially let's say the gearbox case, because of the sheer amount of material to be removed as well as the complexity of it. Especially with all-wheel drive, we actually don't have CAM programs of a lot of our newer parts, so that's something we're actually going to need to do a lot of. So when you do a lot of CNC and CAM stuff, you really learn about how things are manufactured and how like best to make things, and it gives you a lot better of an understanding of physical limitations in the design of a component. It's definitely really cool, specifically operating the CNC machines. Obviously we can't do that now, but ideally for whoever ends up getting MEC 225 approval, as well as like when we're actually back on campus, I do want to train people to run the CNC, and it's very, at times it's very calming, at times it's very stressful because you're worried about crashing the machine. So all in all, it's very interesting work. One thing of note is that you can do CNC/CAM stuff with any other system. Again, as stated in the GBM, it is recommended that you do it with a mechanical system, but if you are an electrical or software person and would like to do it, by all means, definitely. I'm always happy to accept any additional help where applicable. Yeah, that's really all there is for CNC and CAM. So if you're interested in learning a lot more about manufacturing, it's probably something that'll be right up your alley. So that is all of the systems that there are. And I'm just going to go through a few things real quick. After this lesson is over, we're going to pretty much immediately send out a system preference form. You may only, so you can just fill it out immediately. And it'll be due by Friday, September 18th. One stipulation is that in order for you to be assigned to a system, you need to have completed the associated lessons quiz that was mentioned earlier at GBM, as well as you need to have actually watched this. So if you're hearing this right now, you're good in that front, and you don't need to like prove that you've watched this specific lesson. We just want to make sure that everyone understands what they're getting into. We expect system assignments to be posted by the 19th. Not entirely certain about the 19th. If there are complications, we'll have to see, but the date to actually go by would be by the 25th, but ideally no later. Sorry for any confusion there. Yes, so that being said, are there any questions? And again, this part is still being recorded at the moment, so if you're not comfortable being heard in a recording, you can feel free to send a message. So in terms of where the quiz can be found, it will also be sent out on Slack in an announcement following. Yeah, so it'll be on Slack is the short answer.
For the system preference form, what time will it be due Friday? Will it be due at the beginning of the GBM, or will it be due at just 11:59?
Probably 11:59. Actually, that's a good point. We'll specify in the post as to when all these things are due.
Okay.
What other questions are there? Do people have?
I have a question.
Yes.
So you mentioned that we're gonna have a quiz, but you also mentioned in like lesson 1 and 2 that it's not gonna be like these slides aren't like for us to memorize, and it's more like the knowledge that we're gonna get throughout this club is I forgot my train of thought, but how detail heavy is it going to be?
Oh, it's not detail heavy at all. Like seriously, if you like watch the previous lectures, you should be more than fine. It's only 8 multiple choice questions, of which are very easy. I'm pretty sure all of them have at least one joke answer, so that already narrows it down fairly well. It's going to be very general things like, oh, what topics were covered in this lecture, or what is this an example of, like that kind of thing. In terms of where so before I answer any further questions, does that make sense, or is that a good answer or a satisfactory answer?
Yeah.
Cool.
I mean, also keep in mind the lectures are recorded, so you could, if you really can't figure out a question, which, I mean, I don't know if I think you'll be able to. You could just look back at whatever lesson it is.
Also message us.
Okay, so it's posted the whole day. Like we
Uh,
have a whole day to do it?
oh, you'll have a week to do the quiz.
Or
The completion of the quiz is just so that you can be actually assigned to a system. Yeah, so you'll have more than enough time to complete the quiz. It should also take all of like 5 to 10 minutes, so I wouldn't worry all that much about it. For reference for everyone who's asking, the recordings link is posted. It's a YouTube playlist. It's posted in the announcements channel on Slack. I can include all of it again where necessary. What other questions do people have? Oh, in terms of where the system preference form, again, all these forms are going to be sent out right after this. We just wanted to make sure that people didn't start filling it out willy-nilly prior.
And everything of that's going to be posted on the Stony Brook Motorsports webpage, right?
Say that again?
Everything what you've mentioned, including the quiz, and the system preferences form will be posted on the Stony Brook Motorsports website. Is that right?
So the recordings themselves will not be posted, or sorry, the recordings themselves are posted on the website. However, the forms are not, because we don't want people just randomly accessing it. Plus, we're also trying to really emphasize that people really use Slack more often. Slack is our primary mode of communication, and especially as things start picking up, and especially as you're assigned a subsystem, we expect that people check Slack generally about, or like at least once a day, just so that, to be sure that they're getting all the necessary information. So definitely check Slack as much as possible. In terms of the videos, we can look into embedding the videos on the website, but worst comes to worst, on the very front page is a link to it. Yes, there's also a phone app for Slack, so if that is also something that is helpful, that is good. Are there any other questions?
When is the quiz going to be due? On next Friday and also at 1:59 p.m.?
Yeah, probably. Yeah, probably just because that's like when we'd start assigning people systems and whatnot.
Is the quiz going to be on some Google form?
Yeah, it's a Google form. It's a Google form.
Okay. So you'll know. So you'll know immediately once you complete the quiz.
Yes. Yes. Passing criteria will be determined. Again, we're not doing this to be like sticklers. We're really just doing this to ensure that people are understanding things, especially so that like we don't have to go through and reteach, like completely introduce something. Like, let's say if someone mentions stress concentration, someone's like, I have never heard of that before. Well, it was in the lectures. Again, you don't have to know the specifics of it. Again, know that it exists. Likewise, especially for, let's say, the first lesson, which is the design cycle, just have a general understanding of that. Know, like, what is the process? Are you just designing and building something, or is there more to it? Because that's really what drives the team. Yeah. What other questions are there before? Yeah, what other questions are there?
Someone asked this kind of random question, but I can't pronounce his name properly, but anyway, he says, if I fail the quiz, do I get kicked off the team?
Oh, he's just joking. He was the VP last year. He's memeing on us. No, by no means you won't get kicked off the team. We're
You do
again,
get
we're not.
40 lashes though.
Wait, what?
No, I'm kidding. I said you get 40 lashes.
Anyways, jokes aside, again, we're not doing this to like mess with people. We're not doing this to like stress people out. We're just trying to be sure that what we're doing is getting across to people, and that we don't have to that we won't necessarily have to spend too much time going over things which we might have already gone over, just even at a base level. So again, like if someone really pulls up and we're saying like, oh, we have to do this because it makes sense and like it's something that is necessary for the design cycle. We don't want someone to just be like, what's the design cycle? Is that like a unicycle? Um, like that kind of very basic level stuff. You'll see it as you get to the quiz, and you'll be like, oh, okay, this is not all that bad. If we find that everyone's failing it, then we're obviously gonna have to reevaluate how we're determining it. But as it stands, between just it's like very, very light stuff.
Yeah, the quiz just makes sure everybody has a basic understanding coming into doing actual work. That's pretty much it.
All right. Any other questions? So, real quick, my dog is doing well. Uh, in terms of what Geo9 does, it creates sadness. Can we see him? Unfortunately, not, because he's in the other room. And then how many subsystems can we request? So, actually, that's a good point. We would really like you to stay with one system, especially in the event, like, let's say you're in two systems and like the scheduling overlaps or there's just a lot of work for a system. If you would be interested in doing multiple, aside from just like a system that is not CNC and CAM and CNC and CAM. So like, let's say if you wanted to do vehicle dynamics and powertrain, message me. I'll also specify that in the form, and I'll edit the form quickly before I send it out to give that option of saying like, add any other comments, including if you want to be in two systems. We don't encourage it, but if you think if you think you'll be very interested in both of these things and want to pursue both of them, by all means, yeah.
A quick note on that: people generally seem to prefer sticking to one system, as it becomes much more manageable to learn everything about one component or system. So it just becomes easier on yourself and more manageable on yourself to just stick to one system.
Yes.
That's generally just what people find themselves to prefer.
Yeah, I meant requesting on the form, but it's good to know.
Yeah, the form isn't really equipped to handle like requests for both at once. So just put them as like 1 and 2 and message the appropriate people.
Yes.
There's no harm in that.
Of note on the form, you'll have all the choices and you'll be able to rank them from 1 to 6, 1 being the top choice, 6 being the lowest choice.
That's what I meant. Thank
Yeah,
you.
sorry about that.
That's cool.
Cool. So are there any additional questions? All right, I will assume that to be a no then. I'm going to stop the recording.